Understanding Windows Architecture and Security Mechanisms. Introduction. Microsoft Windows is one of the most widely used operating systems across the world. Its popularity stems from its user-friendly interface, broad hardware support, and powerful capabilities. However, underlying this convenience is a complex architecture designed to ensure performance, reliability, and security. This document explores the architectural components of Windows and its integrated security mechanisms in detail. Part 1: Windows Architecture. 1.1 Layered Architecture. Windows follows a layered architecture, with clear distinctions between user mode and kernel mode, ensuring separation of concerns and robust system protection. User mode, where user applications and environment subsystems run. Kernel mode, hosts core operating system components and has unrestricted access to hardware. 1.2 System Components. 1.2.1 Executive Services. The executive is a set of components running in kernel mode responsible for various system-level functions. Object Manager manages Windows objects like files, devices, processes. Process Manager manages process and thread lifecycle. Virtual Memory Manager handles memory allocation and paging. I/O Manager coordinates I/O operations across devices. Security Reference Monitor (SRM) enforces access checks and audit logging. Plug and Play Manager detects and configures hardware. Power Manager manages power usage and states. 1.2.2 Kernel. The Windows kernel is responsible for low-level tasks such as thread scheduling, interrupt handling, and synchronization primitives. 1.2.3 Hardware Abstraction Layer (HEL). HEL provides a consistent interface to hardware, abstracting differences across processor and platform architectures. 1.2.4 Device Drivers. Drivers are kernel mode components that enable communication between the OS and hardware. 1.2.5 Windows Subsystems. These subsystems offer application programming environments. Win32 Subsystem, the main interface for GUI and console applications. POSIX Subsystem, deprecated supported Unix applications. Windows Subsystem for Linux, WSL allows native execution of Linux binaries. Part 2: Windows Security Architecture. Windows security is integrated into the architecture and comprises multiple layers, including authentication, access control, auditing, and encryption. 2.1 Security Model. The Windows security model is based on discretionary and mandatory access controls and is centered around the following. Security principles: users, groups, services with security identifiers, SIDs. Access tokens represent the security context of a process or thread. Security descriptors contain ACLs defining access rules. Access control lists, ACLs. DACL, discretionary ACL specifies who can access an object. SACL, system ACL specifies what access should be audited. 2.2 Authentication and Logon. 2.2 1 Logon Process. 1. WinLogon manages interactive logon. 2. Credential Providers capture credentials. 3. LSAS, Local Security Authority Subsystem Service handles logon validation. 2.2.2 Authentication Protocols. NTLM, NTLAN Manager Challenge Response Protocol. Kerberos, default for domain-based authentication, more secure and efficient. 2.2.3 Single Sign-On, SSO. Windows supports SSO through Active Directory and Kerberos, allowing users to authenticate once and access multiple resources. 2.3 Authorization. SRM, Security Reference Monitor enforces security policies. Access checks, performed when a process attempts to access a secure object. User rights, define what actions a user can perform, e.g., log on locally. 2.4 Auditing. Windows enables audit trails to track user activities and access attempts. Security logs contain records of successful/failed logon attempts, resource access, etc. Group policy allows configuration of auditing policies. 2. 5. Encryption and data protection. Encrypting file system, EFS encrypts files using user certificates. BitLocker, full disk encryption using TPM. POPI, data protection API protects sensitive data like stored passwords. Part 3, Security features and mechanisms. 3.1 User Account Control, UAC. UAC limits the privileges of users and applications. Even if logged in as an administrator, applications run with standard privileges unless explicitly elevated. 3.2 Windows Defender and antivirus integration. Windows Defender, built-in antivirus and threat protection. Smart Screen Filter, checks downloads and apps for malicious behavior. 3.3 Windows Firewall. Integrated packet filtering firewall with inbound and outbound rules. Profiles, domain, private, and public. Rules, configurable based on application, port, IP address. 3.4 Secure Boot. Prevents unauthorized bootloaders from executing during startup using signed bootloaders and firmware validation. 3.5 Virtualization-based security, VBS. Uses hardware virtualization features to isolate critical security components. Credential Guard, protects credentials in an isolated environment. Hypervisor Enforced Code Integrity, HVCI ensures only trusted code runs in kernel mode. 3.6 Windows Hello and Biometrics. Supports facial recognition, fingerprint, and PIN as alternatives to passwords. Part 4, Windows Updates and Patch Management. Security updates are critical for protecting systems against vulnerabilities. Windows Update delivers patches, driver updates, and feature upgrades. WSUS, Windows Server Update Services manages updates in enterprise environments. Part 5, Active Directory and Domain Services. 5.1 Active Directory, AD. A centralized directory service used to manage users, computers, and policies in a networked environment. Domain controllers store and manage the AD database. Group policies enforce security settings and configurations. LDAP protocol used for querying and modifying the AD database. 5. 2 Group Policy Objects, GPOs. Allow administrators to enforce configurations across multiple systems, including password policies, software restrictions, security settings, script assignments. Part 6, Common Threats and Windows Defenses. 6.1 Threat Vectors. Malware, viruses, worms, ransomware. Phishing and social engineering. Privilege escalation. Code injection and buffer overflows. Man-in-the-middle, MITM, attacks. 6.2 Defensive mechanisms. ASLR, address space layout randomization prevents predictability in memory layout. DEP, data execution prevention prevents code execution from non-executable memory regions. AppLocker, controls which apps can run. Windows Sandbox, runs untrusted apps in isolated environments. Controlled folder access, blocks unauthorized changes to protected directories. Part 7, Security Best Practices for Windows. Enable automatic updates. Use complex passwords and multi-factor authentication. Apply least privilege principles. Regularly audit security logs. Encrypt sensitive data. Use centralized security policies via GPOs. Segment network with firewalls and VLANs. Windows, as an operating system, offers a robust and layered architecture designed with security in mind. From low-level kernel features to high-level authentication mechanisms, the platform includes a vast array of components to ensure that systems are resilient to threats and breaches. Understanding Windows architecture and its security infrastructure is crucial for administrators, developers, and security professionals aiming to design and maintain secure computing environments. The Microsoft Windows operating system is a powerful and complex environment designed to support a wide range of applications, devices, and users. It is architected with a focus on compatibility, performance, and especially security. Understanding its internal structure and built-in security mechanisms is essential for system administrators, cybersecurity professionals, and developers. Part 1: Windows System Architecture, Extended. 1.1 Kernel Mode versus User Mode. Windows separates the operating environment into two primary modes to enhance system stability and security. User Mode contains processes such as applications and environment subsystems. Crashes here do not affect the core OS. Kernel Mode hosts the core OS components and drivers. A fault in kernel mode can lead to a system crash, blue screen. 1.2 Process and Thread Management. Process, a container for a set of resources, including memory, handles, and at least one thread. Thread, the basic unit of execution within a process. Windows uses a preemptive, priority-based, round-robin scheduling algorithm, allowing multiple threads to share CPU time efficiently. The Windows scheduler manages thread priorities and handles context switching. 1. 3 Kernel Objects. Windows uses object-oriented principles internally. Everything from files to processes and events are treated as kernel objects. Each object has a security descriptor, a handle table, and reference counts to manage lifetime and permissions. Part 2: System Components and Services. 2.1 Windows Registry. The registry is a hierarchical database storing configuration settings and options. It contains information about hardware, installed applications, system settings, and user preferences. Registry hives include HKUI_local_machine, HKLM. HKUI_current_user, HKCU. HKUI_classes_root, HKCR. Malicious changes to the registry are a common vector for persistent malware. 2.2 Windows Services. Services are long-running background processes that are essential to system operation, e.g., DHCP client, Windows Update. Managed through SCM, Service Control Manager. Services Snap-in, Services.msc. Task Scheduler for time or event-based execution. 2.3 Session and Windows Station. Each user logon session is isolated and includes Windows Station, contains clipboard and desktop. Desktop, holds windows, menus, and hooks. Isolation prevents UI-based attacks, shatter attacks, between user sessions. Part 3: Security Subsystem Architecture. 3.1 Local Security Authority Subsystem, SAS. SAS is a user mode process that enforces the security policy. Functions include user authentication, token creation, audit logging, management of security policies. 3.2 Security Identifiers, SIDs. SIDs uniquely identify security principals, users, groups, or devices. Each access token includes a list of SIDs that are compared against ACLs during access checks. 3.3 Integrity Mechanisms. Windows uses Mandatory Integrity Control, MIC, to enforce different levels of trust. Low integrity, untrusted applications, e.g., Internet Explorer Protected Mode. Medium, standard users. High, administrative processes. System services. Objects are labeled with integrity levels, and lower integrity processes cannot write to higher integrity objects. Part 4: Windows Security Technologies, Advanced. 4.1 Secure Boot and Measured Boot. Secure Boot ensures only signed, trusted bootloaders are executed. Measured Boot measures each component and logs it for later validation via tools like BitLocker or remote attestation. 4.2 Trusted Platform Module, TPM. TPM is a hardware-based security chip used to store cryptographic keys securely. It supports BitLocker encryption, virtual smart cards, Credential Guard. 4.3 Windows Defender Credential Guard. Credential Guard uses VBS, virtualization-based security, to isolate secrets in a protected environment inaccessible to malware, even with admin rights. 4.4 Windows Hello for Business. Replaces passwords with strong two-factor authentication using biometrics and PINs backed by public key infrastructure, PKI. Part 5, Access Control and Auditing. 5.1 User Rights Assignment. Defined via local security policy or group policy, user rights include: log on locally, access this computer from the network, shut down the system. 5.2 Audit policy. Auditing tracks activities on the system. Configurable through local security policy, secpol.msc. Advanced audit policy configuration. Types of audit events include: log-on events, object access, policy changes, privilege use. Audit data is stored in the security event log. Part 6, Networking and Security. 6.1 Windows Firewall with Advanced Security. Includes support for stateful packet inspection, per application and purport rules, IPsec integration, firewall profiles, domain, private, public. 6.2 IPsec. IPsec can be used for secure communications, especially in enterprise settings. Windows supports transport and tunnel modes, and integrates IPsec policies via group policy. Part 7, Windows Update and Maintenance. 7.1 Patch Management. Windows updates can include security patches, driver updates, feature releases. Enterprises typically manage updates using WSUS, Windows Server Update Services, Microsoft Endpoint Configuration Manager, formerly SCCM. 7.2 Windows Servicing Models. Semi-annual channel, SAC for regular updates. Long-term servicing channel, LTSC for stable environments. Part 8, Active Directory and Azure Integration. 8.1 Active Directory Domain Services, ADDS. Provides centralized authentication, policy enforcement, and identity management. Components include domain controllers, replication services, trust relationships. 8.2 Group Policy. Powerful tool for centralizing configuration, software deployment, password policies, desktop restrictions. 8.3 Azure Active Directory, Azure AD. Cloud-based identity service enabling. Single sign-on, SSO. Multi-factor authentication, MFA. Conditional access policies. Integration with Microsoft 365 and SaaS applications. Part 9, Threat Mitigation Technologies. 9.1 Exploit Protection. Includes ASLR, Address Space Layout Randomization. DEP, Data Execution Prevention. Control Flow Guard, CFG. 9.2 Windows Defender Exploit Guard. A suite of features that includes attack surface reduction, controlled folder access, network protection. 9.3 AppLocker and WDAC. AppLocker, rules based on publisher, path, or file hash. Windows Defender Application Control, WDAC uses policy-driven control to allow or block code execution at kernel and user levels. The Windows operating system has evolved into a secure and modular platform suitable for both enterprise and personal computing. Its architecture is deeply layered to maintain performance and isolation, while its security mechanisms span authentication, access control, encryption, and threat prevention. By continuously improving its architecture and integrating advanced technologies like virtualization-based security and cloud identity management, Windows remains at the forefront of secure computing environments. Common vulnerabilities in Windows systems. Introduction. Microsoft Windows, as a dominant operating system in enterprise and consumer markets, is a major target for cyber attacks. Its wide deployment and complex architecture make it susceptible to a wide range of vulnerabilities. These vulnerabilities arise due to misconfigurations, outdated software, poor access control, insecure default settings, or flaws in the operating system's components themselves. Understanding these vulnerabilities is critical for developing effective security strategies and ensuring system integrity. Part 1: Classification of vulnerabilities. 1.1 System-level vulnerabilities. Unpatched operating systems. Microsoft regularly releases patches for newly discovered vulnerabilities. Delayed or skipped patching leaves systems exposed. Kernel exploits. Vulnerabilities in the Windows kernel can lead to privilege escalation or arbitrary code execution. DLL hijacking. Attackers trick applications into loading malicious DLL files, allowing execution of arbitrary code. 1.2 Application-level vulnerabilities. Legacy application support. Compatibility with outdated applications may introduce insecure behavior. Buffer overflows. Improper memory handling in software can lead to code execution or crashes. Scripting vulnerabilities, exploitable through environments like PowerShell or Windows Script Host. 1.3 User-level vulnerabilities. Weak passwords. Users frequently select simple passwords, making brute force and dictionary attacks viable. Phishing and social engineering. Windows users are frequent targets for deceptive emails and websites. Privilege misuse. Users or malware exploiting unnecessary admin privileges can compromise systems. Part 2: Common Windows vulnerabilities. 2.1 Privilege escalation. 2.1.1 Unquoted service paths. Services with improperly quoted file paths can allow attackers to execute malicious programs placed in predictable locations. Example: if the path c:/program files /my app/appservice.exe is not enclosed in quotes, Windows may attempt to execute c:/program.exe. c:/program files /my.exe. 2.1.2 Insecure permissions on services. Improper permissions on services may allow users to modify the service binary or configuration, potentially leading to code execution with system-level privileges. 2.1.3 Token impersonation. Attackers can hijack access tokens of higher privileged processes, gaining elevated access without needing passwords. 2.1.4 UAC bypass. User account control, UAC, is designed to limit the privilege level of applications. Certain design flaws and bypass techniques allow malware to silently elevate privileges. 2.2 Remote code execution, RCE. 2.2.1 SMB vulnerabilities. Eternal Blue, MS17-010 exploited by WannaCry and NotPetya ransomware, targeting vulnerabilities in SMBv1. SMB relay attacks allow attackers to intercept and manipulate SMB authentication. 2.2.2 RDP vulnerabilities. Bluekeep, CVE 2019-0708 critical flaw in remote desktop services that allows RCE without authentication. Credential harvesting. Improperly secured RDP connections can lead to credential theft via keylogging or memory scraping. 2.2.3 DCOM and COM interfaces. Improper access to distributed COM objects can result in code execution, particularly in older systems and unpatched environments. 2.3 Authentication and credential vulnerabilities. 2.3.1 Pass the hash, PTH. An attacker with access to hashed credentials can reuse them to authenticate without knowing the actual password. 2.3.2 Pass the ticket, PTT. Uses Kerberos ticket replay to impersonate users or services across the domain. 2.3.3 Credential dumping. SAS process dumping extracts passwords, hashes, and Kerberos tickets. Tools like Mimikatz are commonly used for this purpose. 2.3.4 Cached credentials. Windows stores hashed versions of credentials to allow offline login. If improperly secured, these can be extracted and reused. Exploitation techniques in Windows, buffer overflows, DLL hijacking, and related attacks. Introduction. Modern cyberattacks often rely on exploiting underlying vulnerabilities in software and operating systems. Among the most well-known and historically impactful of these are buffer overflows and DLL hijacking. These techniques, while rooted in fundamental flaws, remain relevant today, especially in environments running legacy software or systems that lack modern protections. In this document, we examine in detail how these vulnerabilities work, how they are exploited, and what mitigation strategies exist to counter them. Part 1: Buffer Overflows. 1.1 Overview of buffer overflows. A buffer overflow occurs when a program writes more data to a buffer, a sequential region of memory, than it can hold. This overflow can corrupt adjacent memory, crash the program, or enable execution of arbitrary code. Types of buffer overflows: stack-based overflow, heap-based overflow, integer overflows, leading to buffer overflows. 1.2 Stack-based buffer overflow. A stack-based overflow targets the function call stack. By overflowing the buffer, an attacker can overwrite the return address to redirect execution to malicious code, local variables or saved registers. Example in C. Void vulnerable. Char buffer, 100. Gets, buffer, / dangerous, no bounds checking. 1.3 Exploiting stack overflows. Steps. 1. Overflow buffer with data and a carefully crafted payload. 2. Overwrite the return address with the address of the attacker's code or a system function, like system. 3. Gain control of program flow. Payload types include shellcode, injected machine instructions, e.g., spawn a shell. ROP chains, return-oriented programming techniques bypassing DEP and ASLR. 1.4 Heap-based buffer overflow. Occurs in dynamically allocated memory, heap. Exploiting heap overflows involves overwriting heap metadata, corrupting function pointers or virtual tables, exploiting use after free vulnerabilities. More complex but often harder to detect. 1.5 Common mitigations. DEP, data execution prevention, marks certain regions, like the stack, as non-executable. ASLR, address space layout randomization, randomizes memory address layout. Stack canaries, adds a known value before return address to detect overflow. Safe functions, use strncpy, sprint, etc., instead of unsafe functions like gets, strcpy. Part 2, DLL hijacking. 2.1 Overview. DLL hijacking, dynamic link library preloading attack, occurs when an application loads a DLL from an insecure location, allowing an attacker to substitute a malicious version. 2.2 How DLL loading works. When a program loads a DLL, it searches for it using the DLL search order. 1. The directory from which the application loaded. 2. The system directory, C:\Windows\system32. 3. The 16-bit system directory. 4. The Windows directory. 5. The current working directory, CWD. 6. Directories listed in the path environment variable. If an attacker places a malicious DLL in a directory searched earlier than the legitimate one, it may be loaded instead. 2.3 Types of DLL hijacking. Classic DLL hijacking. Application tries to load a DLL from CWD or relative path. Search order hijacking, abuses Windows search logic. Phantom DLL hijacking, app references a non-existent DLL, attacker creates it. Signed binary proxying, LOL-bin, using trusted binaries that load attacker-controlled DLLs. 2.4 Exploiting DLL hijacking. 1. Identify application behavior, e.g., using process monitor. 2. Detect missing or insecurely loaded DLLs. 3. Place malicious DLL in location of choice. 4. Wait for application to load the malicious DLL. DLLs can be used to execute arbitrary code, spawn backdoors or reverse shells, capture credentials or keystrokes. 2.5 Persistence via DLL hijacking. Attackers use DLL hijacking to maintain persistence by replacing DLLs in auto-starting applications, hijacking DLLs loaded by services or scheduled tasks. Part 3, Related exploitation techniques. 3.1 Return-Oriented Programming, ROP. A modern technique to bypass DEP. Leverages existing code snippets ending in RET, gadgets. Chains them to perform arbitrary operations without injecting code. 3.2 Structured Exception Handler, SEH, overwrites. Windows uses a structured exception handler mechanism for crashes. Attackers can overwrite SEH records on the stack. Trigger exceptions to hijack control. 3.3 Format string vulnerabilities. If user input is improperly passed into a format function, e.g., printf input, attackers can read arbitrary memory, write to arbitrary addresses, leak sensitive data. 3.4 Use after free, UAF. Occurs when a program frees memory but continues to use its reference. Exploitation involves allocating controlled data at freed memory location, overriding pointers or control structures. Part 4, Exploit Development. 4.1 Exploit Development Lifecycle. 1. Vulnerability Identification. 2. Proof of Concept, POC. 3. Payload Design. 4. Exploit Delivery. 5. Persistence and Evasion. 4.2 Tools for Exploit Development. Immunity Debugger /x64dbg, for analyzing binaries. Metasploit Framework, for crafting and delivering payloads. Phenom, for generating shellcode. Process Monitor /Procmon, to trace DLL load behavior. Part 5, Real-World Case Studies. 5.1 Buffer Overflow, Code Red Worm. Targeted vulnerable Microsoft IIS servers, via buffer overflow in URL parsing. Spread rapidly and caused widespread denial of service. 5.2 DLL Hijacking, iTunes Vulnerability, 2011. iTunes loaded DLLs from its application directory. Attackers placed malicious DLLs that were executed on startup. 5.3 Windows Search Order Hijack, CD 2015-1641. Used a malicious Word document to drop a DLL. Word then loaded the attacker's DLL due to search order precedence. Part 6, Detection and Prevention. 6.1 Detecting Buffer Overflows. Monitor application crashes. Use fuzzing tools to test inputs. Employ static/dynamic code analysis. 6.2 Detecting DLL hijacking. Monitor unexpected DLL loads via sysinternals tools. Set Windows registry key, safe DLL search mode = 1. Check application manifests for hard-coded paths. 6.3 Prevention best practices. For developers. Use secure coding standards. Validate all input lengths and types. Avoid unsafe functions, strcpy, gets, scanf, etc. For admins. Enforce software whitelisting. Use Windows Defender Exploit Guard. Configure system to prefer known DLL paths. System hardening. Enable ASLR, DEP, Control Flow Guard, CFG. Block unsigned or unknown DLLs via AppLocker or WDAC. Part 7, Industry Trends and Challenges. 7.1 Fileless Exploits. Modern attackers combine these techniques with fileless malware, making detection harder. For example, hijacked DLLs loaded into memory via PowerShell. 7.2 Living off the land binaries, LOL bins. Trusted Windows binaries like Rundle32, Regs432, or Msta can load DLLs or execute scripts without dropping files. 7.3 Exploit Kits and Automation. Exploit kits use these vulnerabilities in browsers or document viewers to deploy ransomware or spyware. Buffer overflows and DLL hijacking remain two of the most powerful and frequently used exploitation techniques in modern cybersecurity. While the methods of exploiting these vulnerabilities have evolved, leveraging more stealth, automation, and evasion, they still depend on fundamental oversights in memory and library management. Defenders must remain vigilant, applying both proactive development practices and layered security controls to reduce the risk and impact of such exploits. Exploiting a vulnerable service, Theory and Practice. Introduction. In the realm of cybersecurity, services are long-running system or user-level processes that often operate with elevated privileges. In Windows, these services, commonly known as Windows services, are critical for various system functions, ranging from networking and printing to updates and security. Unfortunately, due to misconfigurations, insecure coding practices, or legacy vulnerabilities, these services may become ideal entry points for exploitation. Exploiting a vulnerable service means manipulating such a service to perform unintended actions, such as executing malicious code, escalating privileges, or establishing persistence. This theoretical guide presents an extensive overview of how attackers identify, assess, and exploit vulnerable services, particularly within Windows environments. Part 1: Understanding Windows Services. 1.1 What is a Windows service? A Windows service is a program that runs in the background and performs specific tasks without user interaction. Services are often configured to start automatically at system boot and are typically run under privileged accounts like local system, network service, or local service. 1.2 Service Lifecycle. Installed using SCEXE, registry edits, or service installers. Configured with parameters like binary path, start type, and dependencies. Started/stopped by the Service Control Manager, SCM. Executed with a specific user context and set of permissions. Part 2: Common vulnerabilities in services. 2.1 Unquoted service paths. If the binary path of a service contains spaces and is not enclosed in quotes, Windows parses the path incorrectly, potentially executing a malicious file placed in a preceding directory. Example: Image path, C:\program files /vulnap /service.exe. If unquoted, Windows might execute C:\program.exe. C:\program files /vulnap.exe. 2.2 Insecure service permissions. Services may have weak DACLs, discretionary access control lists, allowing regular users to modify the service binary, change service configuration, replace service executables. 2.3 DLL hijacking via services. If a service loads DLLs from a non-system path, attackers may place a malicious DLL in that path, which gets loaded during service startup. 2.4 Binary path injection. If a service's binary path can be modified by a non-privileged user, the attacker may redirect it to a malicious executable. 2.5 Service executable overwrite. When the service binary is stored in a directory with weak permissions, attackers can overwrite it with malicious code, which is then executed by the service on restart. Part 3: Reconnaissance and enumeration. Before exploiting a service, attackers perform extensive reconnaissance. 3.1 Tools and techniques. SC query lists running and stopped services. Mix service list fetches detailed service information. PowerView/SharpView enumerates permissions and service details. Accessed.exe sysinternals check service permissions. 3.2 What to look for. Services running with system privileges. Services configured with unquoted paths. Service binaries located in world-writable directories. Non-default permissions, e.g., everyone, full control. Uncommon or legacy services that are often poorly maintained. Part 4: Exploitation techniques. 4.1 Exploiting unquoted service paths. 4.1.1 Attack steps. 1. Identify service with unquoted path and spaces. 2. Place a malicious executable named program.exe in C:\. 3. Restart the service or reboot the system. 4. Malicious binary gets executed with service privileges. 4.1.2 Mitigation. Always quote service paths with spaces. Use tools like PowerUp or WinPeas to scan for misconfigurations. 4.2 Insecure permissions exploitation. 4.2.1 Types of permissions. Service_change_config. Service_start. Service_stop. write_DAC. 4.2.2 Exploit. If user has service_change_config, they can 1. Modify the service to point to their own binary. 2. Start the service. 3. Execute code with elevated privileges. Tools: scconfig, scstart, PowerShell, set service. 4.3 DLL hijacking via services. 4.3.1 How it works. 1. Service loads a DLL from a local directory or relative path. 2. Attacker places malicious DLL with the same name in the search path. 3. Service loads the attacker's DLL upon startup. 4.3.2 Tools: Procmon, sysinternals, Dependency Walker. 4.4 Executable overwrite. 4.4.1 Scenario: If service binary resides in a directory where non-admins have write access, e.g., c:\program files\vulnap, they can 1. Replace service.exe with malware. 2. Restart the service. 3. Malware runs with system privileges. 4.5 Service installation attacks. Attackers can abuse SCEXE create registry keys, hklm/system/current control set/services/ to create persistent services that execute malicious payloads. Part 5. Real-world exploits and case studies. 5.1 MS06-040, NetAPI buffer overflow. A buffer overflow in the Windows networking service allowed remote code execution with system privileges. 5.2 Eternal Blue, MS17-010. Exploited SMBv1 service on Windows. Enabled remote execution of payloads. Used in WannaCry and NotPetya ransomware attacks. 5.3 Print Nightmare. Vulnerability in print spooler service. Allowed remote code execution and privilege escalation. Part 6. Privilege escalation via services. Services offer attackers a gateway to move from user to system privileges. 6.1 Typical escalation path. 1. Initial foothold, e.g., via phishing. 2. Local enumeration identifies insecure service. 3. Modify/start the service. 4. Execute system-level payload. 5. Dump hashes, manipulate registry, or pivot to domain controller. Part 7. Post-exploitation activities. Once a service is exploited, attackers often establish persistence, e.g., creating new services or modifying startup services. Move laterally using stolen credentials. Exfiltrate data. Disable security tools. Part 8. Detection and prevention. 8.1 Logging and monitoring. Enable auditing for service creation/modification. Monitor event IDs. 7045, a service was installed. 7036, service start/stop. 4697, a service was installed on the system, advanced audit policy. 8.2 Hardening services. Quote all service paths. Set strict NTFS permissions on binary directories. Regularly review service DACLs. Disable unused or legacy services. 8.3 Tools for defense. Windows Defender Application Control, WDAC. AppLocker prevents unauthorized binaries. Group Policy enforces service restrictions. Exploit Guard monitors suspicious activity. Part 9. Penetration testing methodology. 1. Discovery. List all services. Check user context. 2. Analysis. Review permissions. Locate potential paths and binaries. 3. Exploitation. Craft and deploy payload. Trigger service. 4. Post-exploitation. Gain persistence. Clean up logs or establish covert channels. Part 10. Defense in-depth strategy. User awareness. Teach users to avoid social engineering traps that deliver initial malware. Patch management, regularly update services and their dependencies. Least privilege, run services under accounts with minimal required permissions. Segmentation, isolate critical services within network segments. Incident response, prepare to identify, contain, and recover from service exploits. Exploiting a vulnerable service is a critical technique in both offensive security operations and real-world cyber attacks. It enables attackers to escalate privileges, establish persistence, and gain control over sensitive systems. Through careful reconnaissance, vulnerability exploitation, and post-exploitation maneuvering, attackers can manipulate Windows services to their advantage. However, with vigilant monitoring, secure configurations, and layered defenses, such risks can be significantly mitigated. Understanding the tactics used in service exploitation is the first step toward building resilient and secure computing environments. Using Metasploit for Windows exploitation, theoretical overview. The Metasploit framework is a powerful and widely used open-source platform that provides tools for developing, testing, and executing exploit code. It plays a crucial role in penetration testing and ethical hacking, particularly for targeting Windows systems, which are commonly found in enterprise environments. 1. What is Metasploit? Metasploit simplifies the process of exploiting vulnerabilities by offering pre-built modules and payloads. Its key components include exploit modules, code targeting specific vulnerabilities. Payloads, code delivered after successful exploitation, e.g., reverse shells. Meterpreter, an advanced in-memory shell for post-exploitation. Auxiliary modules, scanners, fuzzers, and information-gathering tools. Post modules, used for privilege escalation, data collection, and persistence. 2. Exploiting Windows with Metasploit. Step 1. Reconnaissance. Using tools like map or Metasploit scanners, attackers identify open ports, services, and OS versions to find weaknesses. Step 2. Vulnerability identification. Attackers search for known vulnerabilities, e.g., MS17-010, print nightmare, that match the system's software and configuration. Step 3. Exploit selection. Metasploit contains various Windows exploit modules. For example, exploit/Windows/SMB/MS17_010_eternal blue. Step 4. Payload configuration. Attackers choose payloads such as Windows/Meterpreter/reverse_TCP, allowing remote access once the exploit succeeds. Step 5. Exploitation and shell access. If successful, a shell or Meterpreter session is opened, granting control over the system. 3. Post-exploitation. Once access is gained, Metasploit enables a wide range of actions. Privilege escalation, gaining system-level access. Persistence, creating backdoors or modifying registry keys. Data extraction, dumping password hashes or capturing screenshots. Lateral movement. Attacking other systems in the network. 4. Evasion and defense. Attackers use obfuscation techniques, e.g., encoding payloads, to bypass antivirus and endpoint detection. Defenders must monitor for suspicious activity, enforce patching, and disable unnecessary services. 5. Ethical considerations. Metasploit should only be used in authorized environments. Unauthorized use is illegal and unethical. Security professionals use it to test defenses and improve resilience against real-world attacks. Metasploit streamlines Windows exploitation by combining vulnerability assessment, payload delivery, and post-exploitation into a unified framework. Understanding its theoretical basis helps security practitioners conduct effective tests while helping defenders anticipate and mitigate attacks. Defending against Windows exploits, mitigation strategies. Introduction. The Windows operating system, due to its vast user base and complex architecture, remains a prime target for cyber attackers. Exploits targeting Windows vulnerabilities can have widespread consequences, including data breaches, ransomware attacks, and privilege escalation. As threat actors continually refine their techniques, defenders must adopt a layered, proactive, and strategic approach to security. This essay explores the nature of Windows exploits, common attack vectors, and comprehensive mitigation strategies designed to prevent, detect, and respond to these threats. 1. Understanding Windows exploits. 1.1 What is an exploit? An exploit is a piece of code or method that takes advantage of a vulnerability in software or hardware to achieve unintended behavior such as gaining unauthorized access, executing arbitrary code, or escalating privileges. 1.2 Categories of exploits. Remote code execution, RCE, allows attackers to run malicious code remotely on a target system. Privilege escalation gains higher-level permissions, often moving from a user to an administrator. Denial of service, DOS disrupts services, leading to crashes or resource exhaustion. Information disclosure exposes sensitive data, often paving the way for further attacks. Security feature bypass circumvents protective mechanisms such as firewalls or encryption. 1.3 Exploit lifecycle. 1. Discovery, vulnerability is found. 2. Weaponization, exploit code is created. 3. Delivery, exploit is delivered to the victim. 4. Execution, code is executed on the system. 5. Persistence, backdoors or payloads ensure continued access. 6. Control and exfiltration, attacker takes control and extracts information. 2. Common attack vectors on Windows. 2.1 Unpatched software. Unpatched systems are the most common entry point for Windows exploits. Zero-day vulnerabilities are especially dangerous due to the absence of a fix. 2. Phishing and social engineering. Attackers exploit human psychology to deceive users into opening malicious attachments or links that exploit Windows vulnerabilities. 2.3 Malicious documents and macros. Word or Excel documents embedded with VBA macros can execute shellcode upon opening. 2.4 Network-based exploits. Exploits such as Eternal Blue target SMB vulnerabilities to spread laterally across networks. 2.5 Malicious drivers and kernel exploits. Poorly written or malicious drivers can compromise the Windows kernel, leading to complete system takeover. 3. Windows Security Architecture Overview. Understanding the Windows security model helps in crafting effective mitigation strategies. 3.1 User Account Control, UAC. Prevents unauthorized changes by prompting for administrator credentials. 3.2 Windows Defender and Security Center. Built-in antivirus and system health monitoring. 3.3 Security Support Provider Interface, SSPI. Manages authentication protocols like Kerberos and NTLM. 3.4 Patch Management. Windows Update provides a centralized mechanism to deploy security patches. 4. Mitigation strategies. 4.1 Patch and Update Management. 4.1.1 Strategy. Enforce automated patch deployment via WSUS or SCCM. Prioritize zero-day and critical patches. 4.1.2 Best Practices. Test patches in staging environments. Schedule maintenance windows for critical infrastructure. 4.2 Application whitelisting. 4.2.1 Strategy. Allow only approved applications to execute using Windows Defender Application Control, WDAC, or App Locker. 4.2.2 Benefits. Blocks unknown malware. Reduces attack surface. 4.3 Privilege Management. 4.3.1 Strategy. Implement the principle of least privilege using group policy and role-based access control, RBAC. 4.3.2 Tools. Microsoft Labs for local admin password management. Just Enough Administration, JEA, for PowerShell. 4.4 Network segmentation and firewall rules. 4.4.1 Strategy. Isolate critical assets from general users. Implement granular inbound and outbound firewall policies. 4.4.2 Tools. Windows Defender Firewall with advanced security. Group policy-based network isolation rules. 4.5 Exploit protection mechanisms. 4.5.1 Data execution prevention, DEP. Prevents execution of code from non-executable memory regions. 4.5.2 Address space layout randomization, ASLR. Randomizes memory address locations to hinder buffer overflow attacks. 4.5.3 Control Flow Guard, CFG. Detects and prevents indirect function calls to potentially malicious code. 4.6 Endpoint detection and response, EDR. 4.6.1 Strategy. Deploy EDR tools that provide real-time monitoring and response capabilities. 4.6.2 Features. Behavioral analytics. Incident response automation. 4.7 Secure configuration baselines. 4.7.1 Strategy. Apply CIS or Microsoft Security Compliance Toolkit baselines. 4.7.2 Implementation. Harden services, ports, and protocols. Disable legacy components, e.g., SMBv1, Telnet. 4.8 Attack Surface Reduction, ASR. Rules. 4.8.1 Strategy. Use Microsoft Defender's ASR rules to block executable content from email and web. Office macros from the Internet. Process creation from suspicious applications. 4.9 Malware and threat intelligence. 4.9.1 Strategy. Subscribe to threat feeds and share intelligence via MISP or STIX/TAXII protocols. 4.9.2 Integration. Feed data into SIEM and correlate with local indicators. 5. Case studies of real-world exploits and defense. 5.1 Eternal Blue, CVE 2017-0144. Exploit, SMBv1 RC used by WannaCry and NotPetya. Mitigation, disable SMBv1, patch MS17-010, segment networks. 5.2 Print Nightmare, CVE 2021-34527. Exploit, abuse of the print spooler service for RCE. Mitigation, disable print spooler on non-printing devices, apply Microsoft hotfixes. 5.3 Zeralagon, CVE 2020-1472. Exploit, privilege escalation via netlagon flaw. Mitigation, patch domain controllers, monitor for anomalous netlagon traffic. 6. Security monitoring and logging. 6.1 Windows event logs. Key logs. Security, ID 4624, 4625, System, Application, PowerShell logs. Tools, Windows Event Viewer, Sysmon. 6.2 SIEM integration. Use platforms like Splunk, Microsoft Sentinel, or QRadar to aggregate and analyze logs. 6.3 Threat hunting. Conduct periodic hypothesis-driven hunts. Look for lateral movement, privilege escalation attempts, and unusual process behaviors. 7. User awareness and training. 7.1 Phishing simulations. Regular simulations train users to recognize and report suspicious emails. 7.2 Policy enforcement. Ensure users are educated on acceptable use, password hygiene, and data handling. 8. Incident response and recovery. 8.1 Preparation. Develop and test incident response playbooks. Identify roles and responsibilities. 8.2 Detection and containment. Use alerts and behavioral analytics for early detection. Isolate affected systems immediately. 8.3 Eradication and recovery. Remove the root cause. Restore from known good backups. 8.4 Lessons learned. Conduct post-mortem reviews and update defenses accordingly. 9. Future-proofing Windows security. 9.10 Trust architecture. Assume breach mindset. Continuously verify identity and access. 9.2 Hardware-based protections. Leverage TPM, secure boot, VBS, virtualization-based security. 9.3 Cloud and hybrid security. Use Microsoft Defender for Endpoint and Microsoft 365 Defender to unify security across environments. Defending against Windows exploits is a dynamic challenge that demands a blend of technical controls, policy enforcement, user education, and continual monitoring. No single defense can stop all threats. A defense-in-depth approach that spans from hardware to software, user to admin, and local to cloud environments is vital. By understanding common exploit tactics and adopting comprehensive mitigation strategies, organizations can significantly reduce their attack surface and strengthen their resilience against evolving threats. Key takeaways and future research, extended theory. Key takeaways. 1. Windows exploits reflect both technical and organizational weaknesses. Exploits often succeed not solely due to technical flaws but because of poor organizational security practices, unpatched systems, overprivileged accounts, and lack of security awareness. Addressing both dimensions is essential for holistic defense. 2. Patching alone is not sufficient. While timely patching remains the frontline defense, it is reactive by nature. Proactive threat modeling, attack surface reduction, and anomaly detection provide essential layers of anticipation and protection. 3. Security controls must be context-aware. The effectiveness of security measures depends on how well they align with organizational context, asset criticality, user behavior, threat landscape, and operational constraints. Blanket policies often fail in dynamic environments. 4. Privilege escalation is a universal goal of exploits. Most Windows attacks aim to escalate privileges, turning local access into administrative or domain-level control. Thus, strict enforcement of least privilege, credential hygiene, and isolation is critical. 5. Defense requires continuous adaptation. As attackers adopt new tactics like fileless attacks, supply chain compromise, or living off the land binaries, LOL bins, defenders must constantly evolve tools, policies, and detection techniques. 6. Built-in Windows defenses are strong but underused. Technologies like Credential Guard, Device Guard, VBS, and Defender Exploit Guard offer robust protection but are frequently disabled or misconfigured. Proper deployment and maintenance are vital to realizing their full potential. 7. Security is a shared responsibility. IT, security teams, software developers, and end users all share responsibility. Security cannot remain siloed, it must be embedded into system design, IT operations, and corporate culture. Future research directions. 1. Behavioral biometrics and continuous authentication. Research can explore how typing patterns, mouse dynamics, and user behavior can continuously verify identity on Windows systems, thereby reducing reliance on static credentials. 2. Zero-day detection using emulation and sandboxing. Developing systems that use virtualization or emulation to detect suspicious behavior before executing unknown binaries can improve proactive defenses against zero-day attacks. 3. Secure bootstrapping of legacy systems. Many enterprises still run older Windows versions due to legacy applications. Research into secure bootstrapping methods, virtualization wrappers, or compatibility sandboxes can help defend these vulnerable systems. 4. Attack graph analysis and predictive modeling. Utilizing graph theory and AI to model potential attack paths in Windows environments enables defenders to visualize threats and reinforce the most vulnerable nodes preemptively. 5. Quantum-safe secure channels for Windows domains. As quantum computing advances, domain authentication protocols like Kerberos must adapt. Exploring hybrid cryptography models and post-quantum algorithms is crucial to future-proof Windows networks. 6. Red teaming AI for exploit simulation. Future research could leverage generative AI to simulate real-world adversarial techniques, helping defenders test the resilience of Windows systems against advanced persistent threats in a controlled environment. 7. Cross-platform exploit correlation. Many modern environments are hybrid, involving Linux, Mac OS, and mobile devices alongside Windows. Future work should develop correlation engines that track multi-platform exploit chains and provide unified threat intelligence. 8. Energy-efficient security monitoring for enterprise Windows systems. As data centers and edge devices scale, research into low-power, high-efficiency monitoring systems for Windows endpoints will become increasingly important. Key takeaways: continued expansion. 8. The role of identity is central to security. Modern Windows exploits increasingly target identity systems, credential stores, tokens, or authentication flows, rather than just operating system vulnerabilities. Credential theft tools like Mimikatz, Pass the Hash, or Kerberoasting illustrate how identity compromise can bypass traditional defenses. Thus, identity protection mechanisms like multi-factor authentication, MFA, smart card logins, and Windows Hello for Business are crucial parts of a defensive posture. 9. Security must be built in, not bolted on. Security mechanisms retrofitted after deployment tend to be less effective than those embedded from the start. Microsoft's evolution from NTLM to Kerberos, and then to cloud-integrated identity via Azure Active Directory, shows a trend toward more integrated and resilient design. Future OS hardening must begin at the architecture level, not just through reactive patching. 10. Lateral movement is a key indicator of advanced threats. Exploits rarely stop at the initial compromise. Attackers pivot through networks, exploit trust relationships, and use PowerShell or Windows Management Instrumentation, WMI, to evade detection. Monitoring for lateral movement, implementing strong segmentation, and using deception technologies, e.g., honeypots or canary accounts, are necessary to detect persistent threats. 11. Security is a moving target. Attackers adapt to defenses quickly. Techniques like dynamic code injection, sandbox evasion, and obfuscation are constantly evolving. Defenders must similarly embrace agile methodologies in security, frequent updates, red team exercises, and adaptive baselining. 12. The rise of fileless and living off-the-land attacks. Many modern Windows exploits avoid writing files to disk, instead using legitimate Windows binaries and scripts to execute payloads in memory. These techniques bypass antivirus tools that rely on static signatures. Mitigation requires behavioral analysis, memory scanning, and policy-based controls over scripting environments, e.g., blocking unsigned PowerShell scripts. 13. Threat modeling and risk assessment drive effective defense. No system can be 100% secure. Organizations must prioritize protections based on threat modeling, asset classification, and business risk. Aligning mitigation strategies with known frameworks like MITRE ATT and CK or NIST CSF ensures that security efforts are strategic and defensible. 14. Collaboration and threat sharing are critical. The security of Windows systems is a collective effort. Public-private partnerships, vulnerability disclosure programs, and community-driven platforms like VirusTotal, MISP, and Open Threat Exchange, OTX, are critical for timely, actionable intelligence. 15. Human-centric design improves security adoption. Security mechanisms must consider usability. Poorly designed systems that are too complex or restrictive often lead users to circumvent them. Effective security balances protection with operational efficiency and user experience. Future research, further expansion. 9. Adaptive AI for dynamic security policies. Future research can focus on AI-driven systems that learn from user behavior and threat data to automatically adjust firewall rules, privilege levels, or authentication requirements in real time. This creates a more responsive and personalized security model. 10. Forensic readiness in Windows ecosystems. Building systems that are not just secure, but also forensically ready, allows organizations to investigate breaches quickly and accurately. Research into lightweight, continuous forensic logging that respects privacy and performance constraints is an emerging domain. 11. Security metrics and return on investment, ROI. Quantifying the impact of security investments in Windows environments remains challenging. Research should explore standardized metrics that correlate exploit mitigation with tangible business outcomes such as uptime, data loss prevention, and compliance assurance. 12. Gamification and behavioral science for security training. New approaches in user education, such as gamified simulations, psychological nudges, or role-playing scenarios, can dramatically improve adherence to secure practices. Understanding user psychology is key to designing effective human-centric defenses. 13. Digital twins for exploit simulation. Creating virtual replicas of enterprise environments, digital twins, allows for the safe simulation of exploits and the testing of defenses. This emerging field can inform more accurate risk assessment and proactive policy design. 14. Secure AI workloads in Windows environments. As more AI models run on local Windows machines, especially in edge or enterprise deployments, there is a need to secure AI pipelines from data poisoning, model theft, and inference attacks. Future work should integrate secure enclaves, watermarking, and encrypted computation. 15. Resilience engineering in cybersecurity. Instead of focusing solely on prevention, resilience engineering explores how systems respond under stress. Applying this to Windows environments involves designing self-healing systems, automated rollback capabilities, and continuity protocols that maintain service even under attack.